there, wind power students. Welcome to the lecture that's about a little detail that just sort of got thrown away in chapter 1 of your textbook about Betz's Law. Betz's Law is just too important to have that be all we do in a class about wind power in this class. I want to apologize, by the way, it's got to be 85, 90 degrees in my office today. I don't know why the air conditioner is not keeping up, so I apologize that my glasses keep sliding down my nose and so on. It is just really hot in my house today. Anyway, Betz's Law. Betz's Law is this nifty idea that no wind turbine can capture more than 16/27, which is 59.3% of the kinetic energy of the wind. Doesn't matter how you've designed it, doesn't matter what the wind speed is, whatever the current kinetic energy of the wind is, we can only capture about 60% of it. Now, that seems like an important thing to understand in a wind power class, and in fact, if you check the index of the book, you'll see this is the only time in the whole book they mention it. So let's just kind of talk about this. And I mean, the derivation of why Betz's Law is the way it is not the derivation itself. I don't really care that much about derivations. But it brings up two important questions, and that is, why is there a limit to how much of the kinetic energy of the wind I can capture? It seems like I should only make it a 100% efficient wind turbine if I wanted to. Why is there a limit? And if there is going to be a limit, why is it this strange number of 16/27 of the kinetic energy of the wind? So we have two kind of important questions to answer, and as it happens, both of them require some kind of more basic science ideas that I want to make sure we're all on the same page of. Now, so what I've done here is I have made us a little diagram that's going to help us understand the first part of the question. Namely, why is there a limit to the amount of the kinetic energy that the wind turbine can collect from the wind? It seems like you should be able to make a really efficient wind turbine. Why can't you make one that can capture 80% of the kinetic energy of the wind or whatever? Alright, so here I'm working with this picture here, and I worked really hard to try to get all these arrows in here just right and everything. What I have here is I have the windmill here facing into the wind, and wind is approaching the blades. It doesn't matter actually what time, that's why I chose this pretty little Dutch windmill or whatever here, is it doesn't matter what kind of windmill it is, and the wind has some speed as it approaches the windmill, and therefore it has some kinetic energy. And the whole purpose of having a windmill is that the windmill is going to capture some of that energy and use it to produce kinetic energy of the blades themselves, which we then use to make work and so on. And then when the air exits out through the backside of the windmill, it should have it should be slower than it went into the windmill, because some of that kinetic energy of the air has been used to to power the windmill. So let's try to actually work with this here. Now, I use the symbol V here for speed. Meteorologists sometimes use U and sometimes use V. At some point in the future, we'll actually explain why that is. But we're going to use the subscript 1 to mean ahead of the windmill, and 2 to mean behind the windmill. So we have V1 is our velocity before the wind got to the plane of the turbine blades there, and we'll say windmill V2 will be like the speed of the wind after there. Now, we learned already that there is a certain amount of kinetic energy in the air. That's a slide from the previous lecture. And the kinetic energy will be written E-kin for kinetic energy, and we'll have an E-kin 1 for the kinetic energy of the wind, upwind of the turbine. Remember, 1 means upwind. And from our previous slide, we see that that is proportional to the third power of the velocity. So it depends on V1 cubed. And in the same way, there's a certain amount of kinetic energy in the air downwind from the wind turbine. That'll be E-kin 2, because 2 will be our subscript for behind the turbine. And that's going to depend on the velocity 2 cubed. Alright, now, those two kinetic energies presumably won't in general be the same, because the two velocities won't in general be the same. So there's a difference between the kinetic energy ahead, E-kin 1, and the kinetic energy behind, E-kin 2. And therefore the kinetic energy, the difference between those two is ideally what the turbine extracted. It's the difference between the two. Or we could make this a ratio, and we could say that the difference between the energy that is being removed by the turbine, E-kin 1 minus E-kin 2, divided by E-kin 1, will be the fraction of the kinetic energy ahead of the turbine that got extracted by the turbine. This is our number that Betz Law is trying to solve for. This difference between the kinetic energy, how much of the total amount of kinetic energy that approached the station, the windmill, got extracted by it. Betz's Law is going to be telling us that this number here, this ratio, cannot be bigger than 16/27, regardless of the design or the size or the speed of the wind or anything like that. That's really strange. I mean, why can't it be 100%? Or 90 or something like that, but 100 turns out to be the easiest one to think about. Why couldn't this number be 100%? Well, do the math. How would we get this number, this ratio here to be 100%? Well, if you do the math, the only way it's going to happen is if E kin 2 is equal to 0. If there's no kinetic energy to the wind once it goes through the turbine. Well, the only way you could get 0 kinetic energy would be to have the velocity downwind from the turbine V2 be 0. Okay, well, so basically the air would be flowing through the turbine and then have 0 velocity. It would be stopped. The air would have to completely stop after it goes through the windmill. But if the air completely stopped, how would any more air pass through the turbine? There'd be effectively a wall stopping the air from going through the turbine anymore. So if we could somehow think we're going to develop a turbine that could be 100% efficient and change all of the kinetic energy of the air into kinetic energy for the turbine and reduce the kinetic energy downwind to 0, the problem is the turbine wouldn't produce any energy at all because air wouldn't be able to flow through it. Oh, well, see, that would be a useless windmill, wouldn't it? It wouldn't be able to produce any energy. You'd think you'd made a 100% efficient one, but actually it's 100% efficient at producing no energy at all. That doesn't work at all. See, the air downwind from the turbine has to be moving at least a little bit so that it gets out of the way of more air passing through the turbine. And that takes some kinetic energy. That means the air behind the windmill has to be moving at least at some speed, V2. Therefore, kinetic energy 2, the downwind of the turbine, and for that matter, velocity 2, the speed of the wind downwind from the turbine, cannot be 0. And if that number E kin 2 there in that ratio cannot be 0, there's no way to get this number all the way to 100%. Oh, okay. In fact, the power it would be producing if we did would be 0. So, okay. I see why we can't get this to be 100% efficient or so on. Now, before we start figuring out why the efficiency has to be that 16/27, or sorry, is limited to 16/27, let's answer a couple quick questions. So what we've done here is we've finished part 1 of the lecture. We're going to do a couple quick questions, which again, I have no way of tracking. I have no idea if you get the answers right or anything like that. They're purely for your benefit. And then we'll move on to part 2 of the lecture here. So here's question 1. The kinetic energy of the wind upstream from a wind turbine is blank the kinetic energy of the wind downstream from the turbine. A less than, B greater than, or C equal to. How is the kinetic energy upstream related to the kinetic energy downstream? I hope that's not a very hard question, but we'll get a little feedback. Make a choice for one of those 3 options and we'll get some feedback before you move on to a second question about this first part of this lecture.